Hello, AP Calculus class. Welcome to Unit 3, Day 2 notes. I'm going to be going through these notes. I'm warning you today, this is a long one, so have your coffee with you. Take your breaks if you need to. That's the beauty of doing this asynchronously. I just kind of wanted to get yourself going by kind of warming up and practicing a few of the rules that we did last time. So go ahead and just kind of try, maybe row by row, pause me, unpause me so that you can see. Or, just follow along with me, whatever you need to do to help yourself be better. If you want to try the whole page and then unpause me, whatever it is, I'm going to go through them pretty quickly just because I don't want to talk for like the next 3 hours, okay? So let's go through and just practice some alphabetical functions. So if a of x is equal to 5x to the fourth, then we learned last time to take the derivative here, we were just going to bring the 4 down and multiply it by the 5 in front. And that would give me 20x, and then the new exponent would be 3. So b prime of x, the 2 is going to come down. It's going to be 6x to the first minus, now 5x is linear. Its derivative will just be 5. If I was going to find c prime of x, now it's a fraction in front, but that's okay. I'm just going to bring the 6 down. Negative half times 6 is negative 3, x to the fifth, plus 4x to the first, plus, and then that pi is just a constant, so its derivative would actually be 0. Okay, next we have x to the, I think that's a 6. I can't actually read my own typing. Okay, so that would just be 6x to the, oh no, you know what it is? It's e. JK, let me back that train up. Okay, that's not the eraser. There's the eraser. Okay, so if I want d prime of x here, e is just a number, guys. Even though it's an e by itself is just 2.7. So I'm going to bring the e down, and then I'm going to subtract 1 from the e, so that would be the new exponent. Okay, now f of x. Now in the second row, we're getting into those ones where we have a power rule, but it could be disguised. So I'm going to be rewriting functions and then taking derivatives. So I'm going to rewrite this function as 1x to the negative 4, so that I can apply my power rule, and it becomes negative 4x to the negative 5. Remember, minus 1 makes it more negative. And then if I, what I call Gupta, or go back to algebra form, I have negative 4 over x to the fifth. Again, the negative 4 is just a constant. It doesn't have the negative exponent. The only thing being raised to the negative 5 is the x. That's the only thing that's going to move. Okay, I'm going to Graphica this, get it ready for calculus. That's just x to the half. So when I take the derivative here, I get 1/2 x to the negative half, which if I wanted to clean that guy up, now 1/2 is a fraction itself, so I'm going to make the 1/2 there, and then the x to the negative half is going to go to the denominator and become the positive 1/2, which is just square root. Okay, I'm going to Graphica this one. It'd be 1 and then t to the negative, ooh, this is 1/3 because it's the cube root. So then when I take the derivative here, I'm going to get negative 1/3 t, and then negative 1/3 minus 1, negative 1 minus 3 is negative 4, so it'll be negative 4/3. Then I might put this in algebra form. It'd be negative 1 over 3t to the 4/3. Again, it doesn't matter if you want to leave that as a fractional exponent or put it back in radical form. You can also leave the radical in the denominator. Okay, moving right along, j of x. I'm going to rewrite this one. That's 4x to the 2/3 minus 5x to the 1/4. If I put it in exponential form. Now I can find j prime. Ooh, 4 times 2/3 is 8/3. X 2/3 minus 1, 2 minus 3 is negative 1. 5 times 1/4 is 5/4. 1 minus 4 is negative 3/4. So j prime of x is equal to 8 over 3x to the 1/3 minus 5 over 4x to the 3/4. So kind of some trickier ones just to kind of, again, get you used to some negatives and some fractions. Okay, second half. Going through this alphabet quickly again. All right, so if I rewrite this one, now this is k of z, no big deal. So it's z squared plus 7z to the negative 2. Notice that I didn't take any derivatives in this step. I just wanted to rewrite it so that it was all friendly. Now I'm going to find k prime of z, which would be 2z minus 14z to the negative 3. And then if I clean that up, that'd be 2z minus 14 over z cubed. Okay. And you could call that k prime. I could have also been like dk dz if I was feeling slopey. Okay, I'm going to feel slopey here. If I want to take the derivative here, it'd be dm dr. Now that's saying r is the independent, so r is the variable here, which means 4/3 pi is just a constant. So if I think of the constant multiple rule, the derivative of r squared would just be 2r, which then if I clean that up, I'm going to get 8/3 pi r is dm dr. Okay, now for n, I just want you to be very careful here. Sometimes we think, oh, there's negative exponents or fractional exponents, but sometimes things are just constant. So if I were to really think about n of z here, this is square root of 3 times z squared plus 1/3 times x cubed minus 18.2. Okay, now notice here that the independent variable is z. What that means is that every other variable in this function should be treated as a constant. So if I were to find m prime of z, I'm just going to have root 3 times 2z plus all the rest is a constant. It goes to 0. So it just ends up giving me 2 root 3 times z. Now for something like p of x, what I'm going to do first is I'm going to distribute this in so that it doesn't look like a product. We haven't talked about the product rule. That's our goal for today. So for these easy ones, you could just distribute this in. Now, guys, this is x to the half, right? So if I distribute that in to x plus 1, x to the half times x, I would add the exponents. That's going to make that x to the 3 halves. And then 1 times x to the half is x to the half. So I went ahead and put it in fractional exponent form so that I can take my derivative here and get 3 halves x to the 1 half plus 1/2 x to the negative half. And then if I were to clean that up, it'd just be 3 halves square root of x plus 1/2 square root of x. I tend to change the 1/2s back to square roots because I like square roots better. Okay, same with q. So notice here that the input variable is c, which means e is a constant. It's why we don't call functions e or use e as an input variable. But what I'm going to try to do is clean this function up. So I'm going to go ahead and rewrite that as 16c squared. Like I'm going to distribute the square in. And then what I'm going to do before I take the derivative here is I'm going to make this e over 16, because that's the constant, times c to the negative 2. So I'm going to bring that c up and make the exponent negative, and now I'm ready to find q prime. It's going to be e over 16 times, and then negative 2c to the negative 3. So if I want to clean this all up, it'll be negative 2e over 16c cubed. And then I could reduce the 2/16 if I wanted to. Okay, for something like r, again, we have an x on top and bottom. It's kind of similar to p of x, except it's a fraction, which we have not learned how to deal with. So what I would do is break the heart. X squared over x is just x plus 1 over x. Then I can rewrite this to be x plus x to the negative 1, and then take the derivative. So the derivative x would be 1, and then I'm going to bring the negative 1 down and make that x to the negative 2. So I end up with 1 minus 1 over x squared. Okay. Now for s of x, look, we have all these letters. We have x's, a's, b's, and c's, but the independent variable here is x. So all these a's and b's are just coefficients or constant multiples in this case. This x cubed over a, when I take the derivative, it's just 1 over a is the number, and then the derivative x cubed is 3x squared. Plus a over b times 2x minus, now this is a linear term, its derivative would just be c. So if I wanted to clean that up, that would give me 3 over a x squared plus 2a over b x minus c. Okay. Now look at t. all these letters, but the independent variable is x, which means all the a and the b and the 4 is a constant multiple. It's one giant number multiplied by x. This is actually linear, team. Its derivative would just be 4ab squared because the derivative of x is just 1. Okay, so now that your brain is going, we're going to go in and we're going to be adding 8 rules today. You're like, oh my God, Ms. Bowman, you gave us 6 rules last time. Well, 6 of the rules we're learning today are the trig rules. It's really just 2 rules and then the set of trig rules. So we're going to learn these, add it to our repertoire of not having to do the limit definition anymore. We'll go through a couple of applications at the end, and then we'll call it a day. Again, take breaks as you need. This is a long one for me. So I'm going to try to kind of talk fast, but that's the glory of you pausing me, okay? So the product rule. Now, if I wanted to take the derivative of f of x times g of x, okay, what it does not equal is the derivative of f times the derivative of g. And we're going to go through a proof that kind of shows you why. Now, I'm going to prove the product rule. I am not going to prove the quotient rule, but the proof of the quotient rule looks very similar to the proof of the product rule, and it's in the drive, so you'll be able to see it there. So let's start with, let's say we have the function f of x times g of x, right? And I want to find the derivative. So it would be the limit as h goes to 0 of, I'm going to plug in x plus h for x minus f of x g of x all over h. Now, some of you guys are like, Miss Bowman, like, what in the world do you do with this expression? I'm just going to clean that up a bit. There we go. To get something to cancel. Now, we're allowed to do whatever we want mathematically as long as it's equivalent to 0 or equivalent to adding 0 or equivalent to multiplying by 1. The trick with this one, and something I would have never expected any normal person, including myself, to know what to do to start, someone who thought about this problem for months probably figured this out, and we are just, riding on the coattails of their hard work. So what you're going to do is you're going to subtract f of x times g of x plus h and add that same expression in the middle. Oh my gosh, I can't, guys. I just can't right now. In the middle. That way, all we've done is technically added 0 because we added the negative and positive of the same expression. Now you're like, why in the HE double hockey sticks would you do that? Well, someone figured it out. If I break this up, I'm going to break this hard into 2. I'm going to treat these 2 as 1 and these 2 as 1. So if I do that, I would have the limit of f of x plus h, g of x plus h, minus f of x, g of x plus h over h, plus f of x, g of x plus h, minus f of x, g of x over h. Okay? Now, from here, I'm going to look. Ooh, do you see how they have an expression in common? I'm going to pull it out. When in doubt, always pull out. So I'm going to pull out the g of x plus h here times f of x plus h minus f of x over h plus, and then if I look at what they have in common here, they have an f of x in common. So if I pull that off, I'm left with g of x plus h minus g of x over h. Okay. So now, using limit properties, I'm going to take the limit of each piece by plugging in 0 for h. So now look, if I plug in 0 for h here, I just end up with g of x. Okay. Now, if I plug in 0 for h here, I end up with 0 over 0. But guys, look at this for a second. The limit as h goes to 0 of f of x plus h minus f of x over h, that's the definition of f prime of x plus f of x. There's no h to plug in. And then here, if I take this limit, I end up with g prime of x. Welcome, my darlings, to the derivative rule. So let's summarize this. So if I have the derivative, now I am adding here, so adding the order doesn't matter. If I have the product of two functions and I want to find the derivative, it's going to be the first function times the derivative of the second plus the second times the derivative of the first. So it's kind of like you're multiplying each combination of function with derivative. Now, a lot of times in the book, especially in Fedowalk, instead of calling them f and g, they'll call the functions u and v. And they'll say, okay, it's u times dv dx plus v times du dx. And then they're like, oh, let's just write it shorter. It'd be u times dv plus v times du. Okay, so it's the first expression times the derivative of the second plus the second times the derivative of the first. u dv plus v du. So that's what your new chant is, u dv plus v du. I had a student in the past that called it diva vdu. So it's diva vdu. However you want to spell that, I don't even know. Okay, diva vdu. So it's just the first factor times the derivative of the second plus the second factor times the derivative of the first. I like the u and v, and I'll do a couple of examples here. So when I do something, now honestly team, when I see something like this, I might just actually distribute this out. I might go ahead and use the distributive property, clean it up, and then have just a polynomial I can take the derivative of. Since I want to practice using product rule, what I'm going to do is I'm going to say, okay, this is a product of two different functions. The first function I'm going to call u, the second function I'm going to call v. Why u and v? That's a great question. I have no idea, but that's what they do, and that's how I learned, and so that's what I've just kind of gotten used to. And then I like to set it all up. So I say u is x squared plus 1, and v is x to the fourth plus 2x. Then I find the derivative of u, or du, which would just be 2x plus 0. The derivative of v would be 4x cubed plus, linear, so 2. And then to find my f prime of x, I just do a crisscross. So it's going to be x squared plus 1 times 4x cubed plus 2, diva, and then plus v du. So it's u dv and v du. Okay. So let's look at another one. Now g of x here does not look like a product. It looks like a quotient, but I already know that I can bring that x up and make it x to the negative 2, and now I have a product. So here's my u, here's my v. So I'm going to set up my aside. And again, whenever I'm doing these examples, team, you should be pausing me to kind of think through it after the first one. So try this one after I've kind of rewritten it. Try and see if you can get it. And then unpause me while I go through it. Okay, so here I'm going to set up my u is e to the x. My v is x to the negative 2. My du, the derivative of e to the x is e to the x, my favorite. Derivative of v, x to the negative 2 is going to be negative 2, x to the negative 3. Also a pretty good one. Again, remember making things more negative is going to go down. And then we're just going to say g prime of x, the derivative, is u times dv plus v times du, which if I wanted to kind of clean this up, it'd be negative 2e to the x over x cubed plus e to the x over x squared. I could pull out the e to the x if you want and make it negative 2 over x cubed plus 1 over x squared. So that, all these different forms. If you leave your answer like this, guys, they have to accept that on a free response. You never have to clean it up. But what I would say is that if you're going to be doing things like solving something with this derivative or plugging something into this derivative, you want to clean it up into either one of these forms so that it's easier to plug numbers in. Okay, let f of x equal 3uv, where u and v are differentiable functions. Find f prime of 2 if u of 2 is 3, u prime of 2 is 5, v of 2 is negative 4, and v prime of 2 is 1. Guys, they love a problem like this. And so what I would do here is I would say, okay, I don't know what f of x is, but I know its derivative would be the derivative of these functions. So now 3 is a coefficient, constant multiple, so I'm just going to put it in the front. And then I know that the derivative of u times v is going to be u times v prime plus v times u prime. So I write it in general, and then I'm going to plug in 2. So it would just be 3 times whatever u of 2 is times v prime of 2 plus v of 2 times u prime of 2. And then I'm going to say, do I have that information? And the answer to this is yes. U of 2, they told me, is 3. V prime of 2 is 1. V of 2 is negative 4. U prime of 2 is 5. I end up with 3 times 3 minus 20, which is going to give me negative 17 times 3 is negative 51. Or 9 minus 60 if you distribute it in. Okay, so just kind of different ways to do the product rule. Now the quotient rule. Quotient rules are when we have two functions on top of each other. Not a constant and a function, but two functions. So something with a variable on top and something with a variable on bottom. I don't know why I just got so loud. This mic on the surface is not the best either. I apologize. Okay, if I'm doing the quotient rule. Now again, the proof of this, my loves, is in your notes. It's similar to the proof of the product rule, but it's a little more complex because it's a fraction. If I wanted to take the derivative, when you're doing the quotient rule, I need you to channel your inner Drake. Drake sings like 10 years ago, started from the bottom, now we're here. The quotient rule always starts with the bottom function. So what the quotient rule is it's similar to the product rule, except it's a fraction, so it's way more complex. It's going to be the bottom function times the derivative of the top minus, so that's the big difference between dividing and multiplying, is it's minus the top function times the derivative of the bottom, all of that over the bottom squared. Now you're like, where did that bottom squared come from? In the proof, you have to end up getting a common denominator. It comes from that common denominator. Okay, so there is the quotient rule. Now sometimes you'll see it in terms of u and v. So again, it doesn't matter which one I put on top or bottom, but I'm always going to start with the bottom. So it's going to be v du minus u dv all over v squared. Okay, when I'm memorizing this rule, did it this way. Low d high minus high d low all over low low. So you start with the low function, then do the high function, derivative, minus the high function times the low derivative all over the low times the low. So low d high minus high d low over low low. That's the way I studied it and learned it. And even sometimes when I do my asides, I call them low and high as opposed to u and v or f and g. Okay, so let's do an example quotient rule. So notice I can't break a heart here. I can't rewrite it using algebra because there's this addition and subtraction here. So I'm going to have to use the quotient rule. So this is my high function and this is my low function. And when I do my aside, I'm going to do high equals 2x squared plus 7. Low equals 3x minus 1. And then I have d high, which is just derivative, which would be 4x. D low would just be 3. And I have all my parts to find my derivative function. And when I'm finding my derivative function here, again, start with the bottom. So you're starting with low. So 3x minus 1 times d high minus high d low all over low, low. Okay, so let's talk about illegal algebra. I cannot cancel one of these 3x minus 1s out, team. It would have to be in all three parts for us to be able to divide it. If this is a free response question, you could leave this completely like that. But if it's a multiple choice question, they're going to simplify this top. Now, this bottom is the simplest form. Do not distribute that bottom out. It is a waste of your time. What you would need to do, though, is distribute out the top, watch the negative. So that's going to be negative 6x squared, negative 21, and then combine like terms. So 6x squared minus 4x minus 21 over 3x minus 1 quantity squared. And that is what you would see on the AP exam as an answer choice. Okay, so don't distribute out that bottom. Okay, let's look at another one. Find the equation of a tangent line to the graph f of x equals 2x minus 5 over x plus 1 at x equals 0. Okay, so I see equation of the tangent line, and I'm thinking, do I have my point? Do I have my slope? Okay, this is my little checklist. All right, I need the point. So I'm going to find f of 0 to get my point. So if I plug in 0, I get out negative 5, so my point is 0, negative 5. Now my slope, so I did that. Now my slope, I'm going to take the derivative. So to take the derivative here, I'm going to do my high is 2x minus 5. My low is x plus 1. D low would just be 1. That's kind of nice. Ms. Bowman, thank you for giving me linear functions. My D high would be 2. So it's low, start from the bottom, D high minus high, D low, all over low, low. Okay. Now, you can clean this function up right now. You can also plug in your point and then clean it up. It's going to be up to you. I know I just have a derivative function and I need to find the slope at 0, so I'm going to plug in 0 into the unsimplified version, which is just a little easier for me. Okay, and that gives me 2 plus 5 over 1, which is a slope of 7. So now I have y plus 5 equals 7x minus 0, or you could say 7x minus 5 in slope-intercept form. Okay, so low d high minus high d low over low low. Product rule is a do, or whatever you want to do. First d second plus second d first. And again, order doesn't really matter. If you'd rather do second than d first, it doesn't matter. So let's practice using just the product rule and the quotient rule with different representations of functions. Okay, so the algebraic way will be some ways they love to give you numerical representations of functions and graphical representations of functions. So we'll practice both of them. Okay, and again, try these problems first without me, or maybe watch me do the first one, pause me, and then unpause me to see the answer. Okay, if the representation is non-algebraic, if the representation they give you is numeric or graphical, they're going to give you a function like h in terms of other information. So you can see we have an h of x in terms of a combination of f and g of x. Okay, now it's going to be 2 parts to getting full credit here. And if you tried this on your own first, you probably missed this step. You always need to write the general slope function first without. So they want h prime of 1, but before I can get h prime of 1, I need the expression for h prime of x. So I'm going to take the derivative of each piece since it's a sum and difference. The derivative of 3 is 0. Now the derivative of f of x, I don't know what f of x is. I just know it has a derivative and its derivative would be called f prime of x. So I'm just going to write f prime of x minus, now 2 is a constant multiple, so it comes down. And then again, I don't know what g of x is, but I know its derivative would be named g prime of x, whatever that might be. So I'm just going to write the name in place of a rule or an algebraic expression. Now that I have the general form, I'm going to plug in 1. That's going to give me f prime of 1 minus 2 g prime of 1. And then I'm going to find that information on the table. So negative 2 is f prime of 1 minus 2 g prime of 1 is negative 1. Whoop, I end up with a slope of 0. Kind of nice. Okay, so let's try the other three. H of x equals 4 f of x plus 2. So h prime of x here. Now 4 is a constant multiple. The derivative of f of x is f prime of x, plus the derivative of 2 is 0. So now if I want h prime of 1, it's just going to be 4 f prime of 1, which is 4 times negative 2, and that gives me negative 8. Okay. Like, oh, not so bad. Well, it gets a little bit worse, but as long as you can recognize what rule you have to apply, then your life is a little bit easier. So if I look at h of x now, it's f of x times g of x. When you see this, you need to think product rule. Okay. The amount of times I have to write PR on people's tests and quizzes, well, it's virtual. We'll see. I'll have to type it. Okay. PR means product rule. So if I want the derivative here in general, it's a derivative. It's first d times d second plus second times d first. And again, you could do second, like I could switch these to be the different order. It doesn't really make a difference. But now I'm going to find h prime of 1. So it's going to be whatever f of 1 is times g prime of 1 plus g of 1 times f prime of 1. And then I just go to my table for that information. If I can get this to zoom up. So f of 1 is 3. G prime of 1 is negative 1. G of 1, I need to zoom up for that one, is 4. And f prime of 1 is negative 2. That gives me a slope of negative 11. And there we go. All right, last one of these table ones. Now look, I have a fraction with a function on top and a function on bottom. So I am going to use the quotient rule. I'm not going to pay attention to the fact that it's g over f. I know I'm channeling Drake, so when I do the quotient rule, it's low d high minus high d low over low low. Okay. Sometimes you'll see it written like that, or sometimes you'll see it written like this. Okay. That is not a second derivative, that is just f of x squared. It's why when we write a higher order derivative, we have to put it in parentheses. Okay, but now I'm going to find my information. F of 1 is 3, g prime of 1 is negative 1, minus 4 times negative 2 over 3 squared. Now I could leave this number. That is numeric. It could be my final answer, but I'm going to go ahead and clean it up. And I end up getting 5/9. Okay, so there is some numerical examples. Now let's practice some graphical examples. All right, we'll just do a product rule and a quotient rule here. If I have p of x and I want p prime of 1 and p prime of 6, this is why it's necessary to just write p prime of x first, because we want a general rule that we can then apply to both of those situations. So I'm going to do first d second plus second d first. Okay. So now if I want p prime of 1, I'm just putting in 1 where I see x. So f of 1, g prime of 1 plus g of 1, f prime of 1. And now I'm going to use my graph to help me find this information. So the first graph is f and the second graph is g. F of 1 would just be the point at 1, which is just 1 comma 1. And that would be 1. G prime of 1, if I go to the g graph, g prime is the slope. That slope is 1. And I'm just not going to do p prime of 6 or q prime of 6. Yeah, I just don't feel like it. Okay. So g of 1, again, g of 1 would just be the point, that's 3. And then f prime of 1 would be the slope, that would be 0 there. So I end up with just the answer of 1. Okay, if I did 6, it would just be finding the slope at 6, finding the slope of the other graph at 6, the point at 6, the point at 6, all good in the world. Okay, if it's on a linear function, remember, the slope of the line is constant. So if this slope is 1/2 on the linear part, every single point here has a slope equal to 1/2. Okay. All right, now let's go q prime of x here. So q prime of x is low d high minus high d low over low low. Okay, so if I want 1, it's going to be g of 1, f prime of 1, minus f of 1, g prime of 1 over g of 1 squared. Okay, so g of 1 is 3, f prime of 1 is 0, f of 1 is 1, g prime of 1 is 1, g of 1 is 3. So I end up with -1/9. So just some graph examples there. Now if I were to do these two using the graphs, I'm going to have to flip back and forth. But let's say I wanted h prime of 4 here. Okay, so first I need to find h prime of x in order to find h prime of 4. Now notice here that the numbers in front are just constants. That's the constant multiple rule. So when I find h prime of x, it'll just be 3 times f prime of x. I don't have to use the product rule when it's a constant. And then this would be 2g prime of x. So then if I want h prime of 4, it's going to be 3 times f prime of 4 plus 2 times g prime of 4. And now let's go back to the graph and find f prime of 4, 1, 2, 3, 4, which is on the line. So that's going to be 1/2. And g prime of 4, 1, 2, 3, 4 is here. So that's -1. So we have 3 times 1/2 plus 2 times -1. And that is a number, folks. I'm going to leave it. If not, you would have 3/2 minus 2, which you can simplify into -1/2. Okay. But again, numeric expressions you can keep. All right, now j of x, I wanted to do this one because look, we have a function x squared times a function f of x. This is a product rule because I'm multiplying two functions. So if I want to find j prime of x here, my u is x squared and my v is f of x. So it's going to be x squared times dv, which is f prime of x, plus f of x times du, which would be 2x. So I have a combination of like an algebra expression with a function name. So you kind of have to do, like when it's algebra, you actually take the derivative. When it's a function name, you just write the name of the derivative. So then if I want j prime of 6, it's just going to be everywhere I see x, I'm going to put a 6. So 6 squared times f prime of 6 plus f of 6 times 2 times 6. That's going to give me 36 times, now f prime of 6, let's see, 1, 2, 3, 4, 5, 6, oh, it's 1/2, and then f of 6 is 1, 2, 3, 4. So 36 times 1/2 plus 4 times 12. Again, I could leave this, that's numeric as a final answer. If not, I would end up with 18 plus 48, which is 66. Okay, so those are product rules and quotient rules, some applications with tables and graphs, stuff you'll have to practice for homework. Okay, now my darlings, I'm going to give you the 6 trig derivatives. There is a proof for sine in the completed notes on the graph. I don't like this proof because it requires you to know a limit that you don't know. And that's the same with like the e to the x. When we did the e to the x proof, we got it down to like a limit step, but then we had to just know that this limit was 1, and this has the same definition. There's a limit within the proof that just is 1, and you're just supposed to know that, and I think that's ridiculous. So I'm going to help you out because you've seen the derivative of sine. Okay. The derivative of sine of x is cosine of x. There you go. There's your rule. So the derivative of sine is cosine. It's one that you've kind of looked at before, if that helps. Okay, the derivative of cosine is actually negative sine x. Okay, so sine is cosine is negative sine. So one thing I'm going to tell you is that if the function starts with the letter C, the derivative function is always a negative. And that comes in the proof, yes. A proof that you don't understand and you won't understand until way later in life. So I'm just going to have you memorize it. I hate that. Isn't that super annoying as a teacher? Okay, but you make some flashcards, you practice your derivative rules, all is well with the world. You'll get it. Okay, so let's practice using these derivative rules in the context of other situations. And since, we're just going to put it all together now because, that's how Miss BB. All right, so look, we got a function f of x. Notice that it's a fraction with a function on top and a function on bottom. That, my darlings, is a little quotient rule. So if I want to write out my high is sine x. The derivative of high would just be cosine x. Okay, my low is cosine x minus 2. So my d low, the derivative of cosine x is negative sine x. The derivative of 2 would just be 0, so it's just negative sine x. So now I'm going to put it together. Low d high minus high d low all over low, low. Okay, now that is really unclean. And the only thing I want to do is I want to show you that although on a free response you may leave this answer, on a multiple choice you will not see that answer choice. So I'm going to clean this one up for us just so we can see it. Okay, I'm going to distribute this in. So I end up with cosine of x squared, which we generally write the square next to the cos, minus 2 cosine x. And then negative sine x times negative sine x is actually positive sine x squared. So I'm going to put the square there. Now, you will not see this answer choice, but if you look, we have a cosine squared x and a sine squared x being added together. There's an identity where that is equal to 1. So the cosine squared plus sine squared is 1. That's the Pythagorean identity. So they'll always replace any combination of cosine squared plus sine squared as 1. So that would turn into 1 and then minus 2 cosine x. And that's the answer choice that you will see on an AP exam. So just so you were aware, all right, so sine is cosine. What's cosine? Negative sine. I hope you said that because I paused for you to say it, so hopefully you did. Okay. All right, now we have 4 more trig rules. What's nice is that the other 4, sine and cosine kind of go together. And so tangent and cotangent kind of go together, and secant and cosecant kind of go together. So I'm going to show you kind of one of them and just give you the other one. Same with actually I'm just going to give you tangent, and then your homework is part of it's going to be proving secant. So if I wanted to prove the derivative of tangent, I'm going to rewrite tangent as sine x over cosine x. So using the quotient rule. So if cotangent would just be cosine over sine. And now to take this derivative, since I have a low d high, high d low situation, it would just be low d high minus high d low over low low. Okay, now look, I get cosine squared x on top if I simplify it, plus sine squared x on top if I simplify it, over cosine squared x. I cannot cancel these cosine squareds out because of this addition, but I can use the Pythagorean identity to say cosine squared plus sine squared is just 1. So I get 1 over cosine squared. Now, that is the derivative, but a lot of times we don't like fractions. So what we would do here is we would just use the reciprocal identity that 1 over cosine is secant. So it's really just secant squared x. So the derivative of tan x is secant x squared. So secant squared x. So sine, cosine. Cosine, negative sine. Tangent is secant squared, which means cotangent, now I gave you a hint earlier, if I were to find the derivative of cotangent, it's going to be negative, and I know that since it starts with the letter C, but instead of secant squared, because the cosine and the sine switch, your derivative will have a sign on the bottom instead of a cosine, which is going to make it cosecant squared. Okay, and then secant is 1 over cosine, so when you do that proof, you actually end up with itself, so secant is itself times tangent. I always think that secant loves to self-tan. Secant self-tans. It's itself times tangent, so it's just a self-tanner. And then the last one to write down, and then you're going to have to go and study these later, would be cosecant x. So again, these two are kind of grouped together, just like those two are grouped together, just like sine and cosine are grouped together. It's going to be negative since it starts with a C. And then instead of being secant, since it's cosecant, it's itself times cotangent. And again, the same student I had like 4 years ago who was like, that like the dividend, and he only came up with that because he was like, well, if quotient rule gets low d high minus high d low, like product rule should get something, it's only fair. And so then he was like, same with secant. If secant is self-tans, if that's your trick to remember it, Miss Bowman, then we need a trick to remember cosecant. And I was like, whatever, Paul Airy, come up with something. And he was like, okay, cosecant woke itself up on the wrong side of the cot. So he woke himself up on the wrong side of the cot instead of bed. Okay, whatever, just learn them. However, if you come up with like a cool way to remember these, by all means, my love, share. Otherwise, let's just practice some of these rules, and I think there's only, 3 more things. Okay, we're almost there. Miss Bowman's voice is almost gone. It's only 10 a.m. on October 12th, 2020, but here we go. So if I wanted to find the derivative here, I see it's a trig function with sum and difference. I just take the derivative of each piece. The derivative of sine, cosine. The derivative of tangent minus the derivative of tangent is secant squared x. We're done. That's it. Okay. Gotta love a sum and difference. Ooh, but this one, yikes, Miss Bowman, this one is a product rule. That's okay. We can handle it. We're pros at product rule now. Here's my u, here's my v. If you need to do your aside, by all means, do your du. The derivative of sine is cosine. Do your dv. The derivative of cosine is negative sine, and then do your flip-flop. So it's going to be u dv plus v du. Now, when I clean this one up, I end up with negative sine squared x plus cosine squared x. Guys, that is not equal to 1, and it is not equal to negative 1. These would both have to be a negative that I could factor out to get sine squared to be a negative 1. This one is just this, and that is the answer. Can't do nothing with that. Okay. Now, this is heart-shaped, but it probably doesn't help me to break the heart here, so I'm just going to do my high and my low. So my high here is 3x squared minus cosecant x. So d high would be 6x, and then the derivative of cosecant is negative cosecant x. So that make it plus cotangent x. So it's a self-cotanner. All right, my low is sine x. My d low would be cosine x. And I'm ready to do it. So y prime is low d high minus high d low over low, low. And I'm going to leave that just like that. I'm not going to clean that up. That's as clean as it's going to get. That is our derivative, but do not cancel these signs. All 3 parts have to have a sign for it to cancel. Okay, last one. R of theta. Now, the reason I wanted to give you this one is this is in polar form, if you remember polar functions. But to find the derivative here, we're just treating theta like the x. So it's really no different. So the 4 is just a coefficient. It comes down. The derivative of secant of theta is the same thing as the derivative of secant of x. So it's itself times tangent of theta plus, and then the derivative of cotangent is negative cosecant squared theta. And again, I know these because I've been teaching this 16 years. You're probably going to need a little more practice. Okay, let's try a couple more, and then we'll be done. Find the equation of a line tangent to y equals x tan x at pi over 4. So again, equation of a tangent line, you're thinking to yourself point and slope. Okay. So my point, I'm going to plug in pi over 4 into the OG. So it's everywhere I see x, it gets a pi over 4. So pi over 4 times the tangent of pi over 4. Now pi over 4 is 45, guys. So it's 1 root 2. So the tangent is just 1. So it's pi over 4. Well, that's nice. My point is pi over 4, comma pi over 4. And this is why point slope form is going to become really, really, really friendly for us because of things like this. So now, to find my slope, I need the derivative. Oop, I got to use u dv and v du. I have two functions being multiplied. So u is x. dv would be the derivative of tan x, which is secant squared x, plus v, which is tan x, times the derivative of u, which is just 1 because it's just x, which is kind of nice. And now I'm going to plug in pi over 4. So I end up with pi over 4 times secant squared of pi over 4 plus tangent of pi over 4 times 1. And now I'm going to clean this up. So it's pi over 4, and then the secant is hypotenuse over adjacent, so that'd just be root 2 squared. Tangent of pi over 4 is 1, so that gives me 2 times pi over 4 is 2 pi over 4. That reduces into half a pi plus 1. So there's my slope. So now I'm going to put it in point slope form. So y minus the y equals the slope, and since there are multiple parts to this slope, I need to quantify it, times x minus the x. Point slope form for the win team. Okay, now, last thing. Let's find each of these derivatives. Now, I did use slope notation. So notice how it's the d dx. So this is saying, the first one is saying, find the 999th derivative of cosine of x. The second one here, take the 9th derivative. This doesn't make sense. This makes no sense. Okay. If you're finding the 999th derivative, it needs to match here. So this is impossible. So just a little notation, when you're in slope form and you're taking higher order derivatives, it should be the same number on top and bottom. So now, let's think about how to find the 999th derivative. Like, there's just no way. But good mathematicians look for patterns. So if the function is cosine of x, the derivative would be negative sine x. The second derivative would be the derivative, it's a negative, and then the derivative of sine x is cosine x. The third derivative would be negative, and then the derivative of cosine x is negative sine x. Well, that just leaves me with sine x. And then if I take the fourth derivative of sine x is cosine x. Look, we're right back where we started. It repeats every 4. There was something else in mathematics that repeated powers every 4. I should marinate on that. So let's think about it. If I want the 999th derivative, well, every 4th derivative is going to end up on cosine. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So what I would do is I'd say, okay, what is the closest multiple of 4 to 999, or how many times does 4 go into 999 with what remainder? So 2 with 1, 4 with 5, no. Let's see, that's 1, bring down 4 is 16, that's 39, that'd be 9, 36 with a remainder of 3. Okay, so the remainder of 3 would put us here. The derivative would be sine x. And I'll have you practice one. That was a really tough one just for fun to kind of throw it at you, just so you can kind of see what's going on. But that's all I have for you today. welcome. Congratulations on paying attention. Have a great day, and I'll see you soon.